So the way we represent the two-dimensional xy in Cartesian plane, we can also represent this complex number, and the plane is called as Argand plane. And also the representation we'll see is the form in the polar representation. So Argand plane is nothing but representation of x plus iy. Say you have and this x comma y is the unique point, say pxy, in this capital XY plane. If you want to represent say 2 plus 4i, so 2 and 4, these are the xy coordinate, again minus 2 3, and for this you have 0 1 2 0, minus 5 minus 2 1 minus 2. All these are the coordinates, and you can see the points here exactly like the Cartesian, but here we call this as the Argand plane. So the Argand plane, the modulus of the complex number, that is x plus iy, is nothing but the under root x square plus y square. What is this? This is actually the distance between the origin and the point pxy. So these points on the x-axis, this is going to correspond to the real part, that is a part, or you can write a plus I0, and the y-axis is going to give you the point of imaginary part, say a plus ib, say ib, but take 0 also. So these are the representation in the Argand plane of real axis on the real axis and the imaginary axis. So the representation of the complex number, which is z is equal to x plus iy, and its conjugate. Conjugate means you take negative of anything, you change the sign of this of the I element, so that will be z is equal to x minus iy. So the representation of this complex number in the Argand plane, these are p, this xy, and q, x minus y. And geometrically, if you talk, this point x minus y, this is the mirror image of the point xy on the real axis. Okay. And how about the polar representation of a complex number? We have already seen the polar representation in previous classes. Let us see the polar representation of now the complex number. So if this is pz, we represent it by pz, and this z is nothing but x plus iy. This OP is of length r, and this theta is the angle which this OP is going to make with the positive direction of x-axis. So this r, this is r, and this is theta. We are talking about this r and theta. So this p or p point can also be uniquely represented as r comma theta, which is called the polar coordinates of point p. And this x is given by r cos theta. How? Because this is r, this is theta, this will be r cos theta, this will be r sin theta. So x is r cos theta, as you see here, and y is going to be r sin theta, as you see here. So ultimately what you get is z is equal to r cos theta plus I sin theta. We have replaced x and y with r cos theta and r sin theta. So this particular form is what we are talking about here, and this form is known as your polar form of complex numbers, where this r is nothing but the modulus under root x square plus y square. This is the modulus of z, and theta is called the argument, or you can call it as an amplitude of z, which is denoted by arg, argument of z. So what we are going to do here is, next is, see points. Points are very important. Which angle we are talking about? If it is between 0 to pi, if it is between 0 to pi, or 0 to 2 pi, or between minus pi to pi, there are two variations, minus pi to pi. So if it is 0 to 2 pi, and if it is between minus pi to pi, then this theta, if it is lying between minus pi to pi, we call it as a principal argument of this z complex number. We denote it by argz unless otherwise specified. So what we are talking about here is, this is say figure showing the angle which is between 0 to 2 pi. So if the point is P here, this is theta. If point P is here, this is theta. If point P is here, this is theta. If point P is here, this is theta. Okay, these are different theta versions between 0 to 2 pi. And what about minus pi to pi? So this is theta, but when it comes here in the third quadrant, theta will be taken here, okay, in the clockwise direction, and this will be theta. So these are the thetas. And the next thing is represent the complex number z is equal to 1 plus I root 3 in the polar form. So this 1 is going to be taken as r cos theta, and this root 3 is going to be taken as what? This root 3 is going to be taken as, this one is going to be taken as r sin theta. 1 square plus root 3 square, and on the right hand side we'll add r cos theta square plus r sin theta square, so that will give you r square cos square theta plus sin square theta. 1 square plus root 3 square is 4, and r is going to be under root 4, that is 2. We are not going to take minus 2 value because conventionally this r is going to be greater than theta. So if cos theta, if we place it here, now r we have known, cos theta will become half, sin theta is going to become root 3 by 2, so it gives you theta as pi by 3. Now just place it in the r cos z is equal to r cos theta plus I sin theta. This is your required polar form, and the complex number, which is z is equal to 1 plus I root 3, is now represented here. P, this is 1, this is root 3, this is your theta, and this is your r. Okay, this is how it we represent it. Next example is convert the complex number minus 16 by 1 plus I root 3 in the polar form. How you are going to get it? This is done by multiplying the denominator and numerator by the conjugate of the denominator. So this will be 1 minus I root 3, 1 minus I root 3 multiplication, and this will give you this a square minus b square, so 1 square minus I root 3 whole square. This will be 1 plus 3, 4, and this is going to give you minus 4 plus I 4 root 3. Now we are ready for the polar representation. Minus 4 is going to be r cos theta, 4 root 3, that will be equal to your r sin theta, and you square both sides and add, you will get r, which is equal to 8 square root of 64. So cos theta becomes minus half, sin theta becomes root 3 by 2, and you know that because this is plus, this is minus, this has to be in the second quadrant, so this shows that it is pi by 3. So actually the answer would be pi minus pi by 3. So 2 pi by 3, so it will be r 8 cos theta plus I sin theta. This is the polar form. What about the quadratic equation? By now, by the previous discussion, we have known that for any quadratic equation of the form ax square plus bx plus c, where a is not equal to 0 and these a, b, c are real coefficients of a, b, c, this a square plus b square plus c, it gives you b square minus 4ac, which is the discriminant. We call it as discriminant, and by this we decide what kind of roots are there. If b square minus 4ac is less than 0, we say there is no root. But now we are going to find out the negative real root with the help of the complex number. So the solution would be b square minus 4ac, because it is less than 0. We turn it around, we make it 4ac minus b square, so you get minus inside, minus 1 also. So that we take out I. So our answer would be, two roots will be minus b plus this one and minus b minus this one. Okay. So this we must know, because we have already known that a polynomial equation has at least one root, and a polynomial equation of degree n has n roots. So the quadratic equation has, because quadratic means it is square x square, so it is going to give you 2 values. X cube polynomial give you 3 value, like this. Now let us solve with the help what we have discussed now. X square plus 2 equal to 0. So x square plus 2 equal to 0 means x square is equal to minus 2. So x is what? Plus minus under root minus 2, which is equal to plus minus under root 2i. What about x square plus x plus 1 equal to 0? So this is, just find out b square minus 4ac. b square minus 4ac is what? 1 minus 4, that is minus 3. So this is going to give you minus 1 plus minus under root minus 3 by 2 into 1, which will give you 2 values. Okay, minus 3 means basically this minus 3 is nothing but minus 1 into 3, and if you want to take out the root, that will be equal to root 3, and this is nothing but I, root 3i. How to solve this? Here b square minus 4ac, discriminant you need to find out. This is a, b is 1, c is root 5. A root 5, b 1, c root 5. So just find the discriminant and you'll get it equal to minus 19. And the solution would be minus b plus minus under root 19i by 2 root 5. So this was the discussion on the polar representation, and we're going to take few more of this discussion in the later session. Thank you so much.